Hi everyone, welcome to video 22-1A. We're going to be talking about conditional probability, as you can see in the title of our section here. I'm on page 1137, and you guys, our essential question here is how do we calculate conditional probability? We're going to be doing that for the most part by looking at the idea of a two-way frequency table, which we introduced in the last module. Now, if you remember what a two-way frequency table is, it gives information with a choice going two different ways, basically. So here's our traditional two-way frequency table with the same characteristics that we encountered in the last module, which is a study of a new medicine, and that some of the study participants were given the medicine and some were not. So we have two columns that talk about that distinction. And then after a week, the participants were asked whether they experienced a headache or not during the week. And so then we have that condition, headache or no headache. Okay. So conditional probability, as you can see here in our definition at the top, is the probability that event A occurs given that event B has already occurred. And we have this notation here, the probability of A/B, or the probability of A given B. So let's talk about how we're going to do this, okay? As we look at our two-way frequency table here, it says let event A be the event that a participant did not get a headache. Let event B be the event that a participant took the medicine. So that is our given condition, is B. First off, to the nearest percent, what is the probability that a participant who took the medicine did not get a headache? So no headache, this is the row we're looking at right here, okay? We need to know how many participants took the medicine altogether. So first off, we're going to look at this first column, and that is going to be 65 total participants that took the medicine. So let's put that in the blank there. And then of these 65 in this column, how many did not get a headache? That would be 54 out of those 65. So what conditional probability does for us, basically, you guys, is that it changes our denominator from normally we would take it out of this total number of all the 100 participants to a smaller sample size of just the number of people who took the medicine. So our probability of A given B, and again, remember that's A, that they did not get a headache given that they took the medicine, is going to be 54 out of 65. And we can find that as a decimal and convert to a percent. That's 83%. Then for part B, it says to the nearest percent, what is the probability that a participant who did not get a headache took the medicine? This one is a different given. So we're given that there was no headache. That means we're looking at this second row of our two-way frequency table here. And how many participants did not get a headache? There we want to look at this total number in the far right-hand column, and that is 76 participants did not get a headache. And out of this row of no headache, the conditional probability is that 54 out of those 76 took the medicine. So we're going to fill that in. So the probability of B given A is 54 out of 76, and that's converted to a percent as 71%. So please take note, you guys, that part A is asking you what's the probability that they took, probability that a participant who took the medicine, so this wording right here is indicating me my given did not get a headache. And then part B is what is the probability that a participant who did not get a headache, notice that's my different given amount. And whatever that given condition is, that's what's going to lead to my denominator of the totals. All right, let's look at part C. So part C says, let the number of A be the number of participants who did not get a headache, and then let the number of B be the number of participants who took the medicine. And then let the number of A and B be the number of participants who took the medicine and did not get a headache. So in other words, if we look back at the two calculations we just did, the common number here is 54. And that's the spot right here where we have both conditions being met, both taking the medicine and not getting a headache. So again, if we put those numbers down, the number in A is 76, the number in B is 65, and the number in both A and B, remember that's what that arrow means, is and, the overlap, okay, is 54. So next we're going to express the probability of A given B and the probability of B given A in terms of the number of participants in A, in B, and in A and B. Okay, so let's look back at those calculations again. For the probability of A given B, which is up here, that's our 54, which is the number in both sets A and B. So the number in A and B out of, again, we're back here, probability of A given B was out of 65, and 65 was the probability of B, or the number in just event B. So notice the tie-in there between the given condition becomes the denominator, okay? Then the reverse is also true. The probability of B given A is the number, that's an N, the number of A and B again, because looking back, probability of B given A is here, okay? Here's our 54 again, which we know we're tying into the intersection. So the number of A and B divided by, this time we have divided by, probability given A is out of 76, and 76 ties in with the number of in A. So that is the number in A. So again, look at that second given letter is always going to correspond to that denominator for you. Okay? So that's how we find our conditional probability here from a two-way frequency table. Let's go to the next page. And on the next page, you guys, all I really want to emphasize to you in Explore 2 is that you can develop a formula for the probability of A given B that uses relative frequencies, which are, of course, probabilities, rather than frequencies, which are counts, which was the information that we were using on the first part of this lesson. We were just talking about the number in each section rather than just the probability. And this is just really interesting. It doesn't really take the math in any different direction, so I'm actually going to skip right over into the next video here, but I do want you to know that if you were to go in and fill in all these values, so we're taking all of these values in our two-way frequency table here and making them into probabilities by basically dividing them all by the total. You can write that down, because if you're scaling all these numbers by the same division factor, then basically they're all going to relate to each other in the same way, so it's not going to change the calculations at all. The idea behind the conditional probability is still that you're taking a subsection of the total sample space and finding a ratio, and we'll look at those ratios at the bottom of the page. Let's look at those right now. So part C is just saying that the probability of A given B can be found just in the exact same way as we were before, with these letters here all being N's on the previous page. Now we can say that it's the same thing as the probability in each of those places. And again, it's always the intersection to begin with and divided by whatever the denominator is the given condition. Again, over here, denominator is the same as the given condition. Okay, we would still end up with the exact same probabilities as we did on the previous page. So again, no new math there, just know that you can see those formulas, whether you see them with an N in all those blue circled places or a P for probability, you're still using the same concept. Okay, so we're going to skip into the next video here, and we will see you guys next time.